Hello, my student. We're gonna start with a new chapter, chapter 2, which is transformers. Introduction. A transformer is a device that changes AC electrical power at one voltage level to AC electrical power at another voltage level through the action of a magnetic field. It consists of two or more coils of wire wrapped around a common free magnetic core. These coils are usually not directly connected. The only connection between the coils is the common magnetic flux present within the core. So there is no physical connection between the two coils. One of the transformer windings is connected to a source AC electrical power, and the second transformer winding supplies electrical power to the loads. The transformer winding connected to the power source is called the primary winding or input winding, and the winding connected to the loads is called the secondary winding or the output winding. If there is a third winding on the transformer, it is called a tertiary winding. Okay, we'll move to the next slide. Section 2.1. Why transformers are important to modern life. In a modern power system, electrical power is generated at voltage of 12 to 25 kilovolt, which is high voltage. So transformers step up the voltage to between 110 kilovolt and nearly 1000 kilovolt for transmission over long distances at very low losses. So transformers then step down the voltage to how much? To 1234.5 kilovolt range for local distribution, and finally permit the power to be used safely in homes, offices, and factories at voltages as low as 120 volt, which is low voltage, because as you know, in our homes we need low voltage. Okay, so this is the function here for transformer, to step down the high voltage to low voltage. Okay, let's move to next section, which is 2.2. Types and constructions of a transformer. The principal purpose of a transformer is to convert the AC power at one voltage level to AC power of the same frequency, okay, at another voltage level. Transformers are also used for variety of other purposes, but in this course we will concentrate on the power transformer. Power transformers are constructed on one of two types of cores. One type of construction consists of a simple rectangular laminated piece of steel with the transformer windings wrapped around two sides of the rectangular. This type of construction is known as a core form and is illustrated in figure 2-2. Core form. The other type consists of a three-legged laminated core with the windings wrapped around the center leg. This type of construction is known as shell form and is illustrated in figure 2-3. In either case, the core is constructed of thin laminations, okay, electrically isolated from each other in order to minimize eddy current. The primary and secondary windings in a physical transformer are wrapped one on top of the other with the low voltage innermost, okay? Such an arrangement serves two purposes, okay? Number one, it simplifies the problem of insulating the high voltage winding from the core. It results in much less leakage flux than would be the case if the two windings were separated by distance on the core. Okay, this is the two purpose, very important here. Okay, let's move to next slides. In addition to the various power transformer, two special purpose transformers are used with electrical machinery and power system. The first of these special transformers is a device specially designed to simulate the high voltage and produce a low secondary voltage directly proportional to it. Such a transformer is called a potential transformer. Okay, a power transformer also produces a secondary, also this is a power transformer, reduces a secondary voltage proportional to its primary voltage. The difference between the potential transformer and the power transformer is that the potential transformer is designed to handle only a very small current. The second type of the special transformer is a device designed to provide a secondary current much smaller than but directly proportional to its primary current. This device is called a current transformer. So we have potential transformer, okay, and what current? A current transformer. Okay, also we can see the two types here of the construction of the transformer. Okay, this is the core form transformer construction. As you can see here, this is the primary windings here wrapped around the core here, and this is what here, this is the secondary secondary windings here. Okay, as you can see here, we have VB, V input voltage, primary for primary, and I primary. Okay, and in primary, what is the meaning of in here? This is number of turns for primary, and this is the current here for the primary. Also for secondary, we have NS. This is number of turns in secondary winding, and IS. This is the current in secondary winding, and also VS. This is the voltage for secondary, which is connected to what? To the load. For example, if we have here a load, resistors load. Okay, this is the load. Okay, this is the first type, which is core form. We have another one here, another types, which is shell form transformer construction. Okay, as you can see, the two windings will be in the middle here. As you can see, this is the primary, okay, winding, and this is what here, this is the secondary. This is the shell form. Okay, let's move to next slide. Now guys, here we'll talk about the ideal transformer 2.3. An ideal transformer is a lossless device with an input winding and an output winding. The relationship between the input voltage and the output voltage and between the input current and the output current are given by two simple equations. We can see the figure here, 2.4 shows an ideal transformer. let's make zoom in. This is the ideal transformer, as you can see here. This is VB, voltage for primary, I primary, and this is NB, number of turns for primary, and this is the windings here. This is the coil here. Also here this is the secondary coil, NS, IS, VS. Okay, as you can see, there is no physical connection between what between the primary winding and what secondary windings. Okay, also this is here, as you can see, this is the schematic symbols of a transformer. Okay, as you can see, this is the symbol. If we need to draw the circuit, this is the symbol for transformer. Okay, and also here another symbol. Okay, let's move to the next slides. Okay, the transformer shown in figure 2.4 has NP turns in primary of wire on its primary side and NS turns on wire on its secondary side. The relationship between the voltage VP applied to the primary side of the transformer and the voltage VS produces on the secondary side is, this is the relationship, VP over what? Over VS equal A, where A is defined to be the turns ratio of the transformer. So A equal what, guys? Equal NP over VS. Okay, NB over VS. Okay, define turns ratio. Okay, so NP over no, here guys, here NP A will be equal what? Sorry for the mistake here. NP over what? Over NS. Okay, turns ratio. Okay, so here the relationship between the current IP flowing into the primary side with the transformer and the current IS flowing out of the secondary side of the transformer is what? Is IS over what? Over IP. This is IS equal what? Over IP equal A. Okay, so finally we can summarize these relations as follow. This is very important equation. This is the one here. A will equal what? VB over VS equal what? IS over IP. VB, this is voltage for primary over V voltage for the secondary equal current for secondary over the current of the primary. Okay, we'll use these equations to solve some problems. Let's move to the next slides now here. Power in ideal transformer. Okay, the power supplied to the transformer by the primary circuit is given by the equation Pn equal what? Vp multiply Ip cosine theta p, where theta p is the angle between the primary voltage and the primary current. The power supplied by the transformer secondary, also here we can write the equation for secondary. P out will equal what? V secondary multiply I secondary cosine theta s. Okay, where theta s is the angle between the secondary voltage and the secondary current. Since voltage and current angles are unaffected by ideal transformer, then the primary and the secondary windings of an ideal transformer will have the same angle theta. Okay, because we are talking about the ideal transformer. In other words, the same power factor cosine theta, we can find the relationship between the input power and the output power by rating the output power in terms of the primary voltage and what current. Okay, this is the be out here. Okay, we can write summarize. So P out will be equal what? P Vp Ip cosine theta equal what? Pn. Thus, the output power of An ideal transformer is equal to its input power. The same relationship applies to what? Reactive power, Q, and to parent power, S. So Qn will be what? Vp Ip sine theta. Also will be what? Vs Is sine theta. Okay, now we'll use sine theta for what? For reactive power. So Sn will be equal also Vp Ip equal what? Vs Is equal what? S out. Okay, these equations are very important to we'll use for solving problems in the transformer. Move next slides. Now impedance, a transformation through a transformer. The impedance of a device or an element is defined as the ratio of the phasor voltage across it to the phasor current flowing through it. ZL equal what? VL over what? IL. Okay, this is the impedance. One of the interesting properties of a transformer is that since it changed voltage and current levels, it changed the ratio between the voltage and current, and hence the apparent impedance of an element. To understand this idea, we'll see figure 3. If the secondary current is called Is, the secondary voltage is Vs, then the impedance of the load is giving, also this is the impedance for the load, ZL will equal what? Equal Vs over what? Is, secondary. We'll use what? The secondary quantities. The apparent impedance of the primary circuit of the transformer is what, guys, here? ZL equal Vp over Ip. We'll substitute here, okay, for A Vs over Is. So we'll get what here? We'll use this formula here. ZL will equal what? A square multiply ZL. A square constant, okay, multiply ZL. Now 2.4, theory of operation of real single phase transformers. When a voltage is applied to the primary of a transformer, a flux is what is produced in the core as given by Faraday's law. The changing flux in the core then induces a voltage in the secondary winding of the transformer. Because transformer cores have very high permeability, then the net magnetic force required in the core to produce its flux is very small. Since the net magnetic force is very small, the primary circuit magnetic force must be approximately equal and opposite to the secondary circuit's magnetic force. This fact yields the transformer current ratio. Okay, this is a general information about the theory of operation of the real single-phase transformer. Last section, okay, in this chapter, section 2.5, the equivalent circuit of the transformer. The losses that occur in the real transformers have to account for any accurate model of the transformer behavior. The major items to be considered are: number 1, copper. I square R, losses. Copper losses are the resistive heating losses in the primary and secondary windings of the transformer. They are what? Proportional to the square of the circuit in the windings. Number 2, eddy current losses. Eddy current losses are resistive heating losses in the core of the transformer. They are proportional to the square of the voltage applied to the transformer. Number 3, hysteresis losses are what? Associated with the rearrangement of the magnetic domains in the core during each half cycle. Okay. Number 4, leakage flux. The fluxes, okay, fluxes for primary and secondary leakage, which escape the core and pass through only one of the transformer windings, are leakage fluxes. These escaped fluxes produce a self-inductance in the primary and secondary coils, and the effects of the inductance must be accounted for. Okay, let's move to the last example here for this chapter. Now we'll start solving example 2-1. A single phase power system consists of a 480 volt 60 Hz generator supplying a load Z load equal 4 plus J3 ohm. This is the impedance of the load. Through a transmission line of impedance Z line equal 0.18 plus J 0.24 ohm. Okay, this is the impedance for the line, transmission line. Answer the following question about this system. A, if the power system is exactly as described in the figure 2-6, what will voltage at the load be? What will the transmission line losses be? Next part, suppose a 110 step-up transformer is placed at the generator end of the transmission line, and a 10-1 step down a transformer is placed at the load end of the line. What will the load voltage be now? What will the transmission line losses be now? Now let's start solving this example. Okay, this is the, by the way, this is the figures here we have for this example. As you can see, this is the power system A without and with a transformer in B. This is A. As you can see, this is we have this is the supply, this is generator here, 480 volt with the angle 0, and this is the, by the way guys, this is the transmission lines. Okay, this is with the impedance. Okay, we have the current I line, Z line, 0.18 J 0.24 ohm, and this is the load here, as you can see. Okay, Z load 4 plus J 3 ohm. Okay, for B we will add transformer, as you can see here, T1. Okay, T1 110 and T2. Okay, step down 10 to 1. Okay, we will see now the difference between part A and what part B with the adding a transformer T1 and what here T2. Okay, let's move to the next slide. So solution. A figure 2-6 shows a power system without transformers. Okay, so the first figure without transformers. Here I generator will equal I line will equal what? I load, because series circuit we have here. So the line current in this system is given by what? I line equal what guys? V over Z line plus what? Z load. This is Ohm's law. Voltage over what? Impedance here. Okay, so we have the voltage for 480 with angle 0 volt over, this is the impedance for the line and the load. Okay, we have to add them together here. We have 0.18 and 4, so we have here 4.18. Also plus what? J 3.24. We can add them together. Okay, we can now use the calculator by using the complex mode to find what? The answer here, because we have a complex number now. So the answer will be guys what? 19.8 with the angle what? minus 37.8 ampere. Okay, this is the current now, I line. Therefore, the load voltage is what? Again, Ohm's law here. V load equal what? V load equal I line multiply Z load. Because as you know that I line equal what? I load. Series, okay? We'll use the same current here. So I line 90.8 with here with angle minus 36.8 multiply what? Z load 4 plus J3. Okay? We can convert here, guys, the rectangular form to what? Polar form. So we can do the multiplication. Okay? So I use the calculator here to convert here. It will be what? 5 what? 5 with angle 36.9 ohm. Find the multiplication. So the answer will be what? 5 multiplied 90.8 will be what? 454 with the angle what? With the angle minus 9, minus 0.09. Okay, in multiplication, okay, you can what? You can add the angles. Okay, in multiplication, okay, you have to what? Add the two angles. In division, we have to what? Subtract the angles. Okay, keep in your mind the two things here. Now we can find, finally we can find the line losses here by using what? B losses. Okay, this is the formula here. B losses equal I line square multiply R line. Only the resistors here, R line. Okay, so 90.8 ampere square I line multiply what? 0.18 without J. Okay, guys, without J. Only what? R here, 0.18. So the losses will be 1000. Okay, 484 watt. This is the answer. We already calculate the voltage and what? And the losses in watt. Okay, now let's start B, part B. Okay, here, part B. Okay, so shows 2-6P shows the power system with the transformers. To analyze this system, it is necessary to convert it to a common voltage level. This is done in two steps. Step number 1, eliminate transformer T2 by referring the load over the transmission line's voltage level. Number 2, eliminate transformer T1 by referring the transmission lines eliminates elements and the equivalent load at the transmission line's voltage over the source side. So the value of the load's impedance when reflected to the transmission system voltage is, we will use this formula, guys, Z load, okay, dash equal what? A square multiply Z load. So A square, okay, so we'll use the ratio here. Okay, the ratio for the transformer T2. So 10 over 1 square. Okay, 10 over 1. It is given from the question. Multiply what? Multiply 4 plus, okay, J3. This is for the load. So the answer will be what? 400 ohm plus J300 ohm. So the total impedance at the transmission line level is now is what? Is Z equivalent equals Z line plus what? Z load dash. Okay, so we'll just add them together here. Okay, so it will be what? Here 400.18 plus what? 300.24 J. We will convert now to the what? To the polar form by using the calculator here. 500.3 with the angle what? 36.88 ohm. Okay, guys. Now we'll move to the next step here. Okay. Now the equivalent circuit is shown in figure 2.7. Okay, we'll see the figure. The total impedance at the transmission line level, Z line plus Z load dash, is now reflected across what T1 to the source. Now we'll use T1, okay? We'll use what T1 now to the source generator. So again, the same equation here, Z equivalent A square Z equivalent, okay? A square Z line plus Z load. We have to add the line, okay, with the both Z equivalent. So now 1 over 10 square. 1 over what? 10 square for T1. 0.18 plus what? J 0.24 plus 400 plus 300, okay? So okay, we add them together. So finally we will get what? 5.003 with angle 36.88. Notice that Z load double dash 4 plus J 3 and Z line dash is what? 0.0018 plus what? J 0.0024. The resulting equivalent circuit is shown in figure, okay? The generator's current is now, we'll find what? Generator current, okay? Generator current here, I generator equal what? The same voltage for 80 with the angle 0 over what? 5, now 5.003 with the angle what? 36.88, okay? So the answer will be what? 95.94 with the angle minus 36.88 ampere, okay? Now, knowing the current IG, we can now work back and find I line and I load. Working back through T1 we will get, okay, we'll get now NP1 multiply IG N secondary 1 multiply I line. So I line will be what? NP1 over NS1 multiply what? IG. So 1 over 10 multiply IG, okay, we will get what? I line, okay. Now working back through T2 gives what? NP2 I line, NS2 I load. So I load equal what? NP2 now over NS2 I line. So now 10 over 1 multiply the same current, now 10 over 1, okay, we'll get what? 95.94 with the same angle minus 36.88 ampere. It is now possible to answer the question originally asked. The load voltage is given by, now very simple, you have the current now, V load equal what? I load multiply Z load. You have the I load now, okay, which is 95 with the angle, multiply what? Z load 5 with 36.87. So the answer will be what? 479.7 with angle minus 0.01. And the line losses are given by what? B losses, the same equation here, I line square multiply R line. I line square is what? 9.594 ampere square multiply 0.18 ohm. So the answer will be 16.7 watt. 16.7 watt. As you can see, we reduce the losses here, okay? In part A, we have 1000, okay, losses. Now here, by using the transformer, we reduce the losses to be 16.7 watt only, okay? And by the way, this is the two figures here to show you the equivalent here, equivalent circuit, okay? This is the equivalent circuit, okay? After we eliminate the two transformers here, eliminate equivalent circuit here will be, this is Z load double dash, okay, and this is Z dash line, okay, after we convert, eliminate the two transformers, okay. So thank you students for watching this video and best regards.